For office hours, I'm gonna log in to the chat as well so we can chat like real gamers. But it's not showing me as online. That's weird. Live just now. Yeah, okay, I'm live. Good. Awesome. All right. Perfect. Let's let me kill Slack to get rid of those notifications. Pull up the chat for Zoom. Okay. Awesome stuff. So this is gonna be a Q&A for problems people are having with the reversing homework. One person here saying, could we go over seeing how the input is mangled in GDB? So we have our first question that we're going to dive into. Absolutely. Let's figure that out. All right, so here we have a terminal. Let's SSH in to see what I have. What do I have spun up right now? Yeah, okay, perfect. Well, testing 1 doesn't have mangle. So let's go find a better challenge. Did level 2 have it? Let's take level 3. Level 3 testing 1. Do this in practice mode. Okay, so that's launching, and then let's hit inspect to open it up in Binary Ninja. All right, here we go. So let's see what it's like. We start out, it prints us a bunch of stuff. How does it receive the input? The easier way to determine that is dynamically. Okay, S-trace that. It gets the input from the environment. Awesome. All right, let's. Oh, you can't see my terminal. All right, so I ran it, and it just said, "Hey, there's a environment input." So what is the environment variable? Let's take a look. There should be a call to get env here. Look like smdf, right? So it goes through the environment. We can look at we could look at the what's it called? The provenance of this data. So let's actually go through all the way. So okay, it dereferences variable. Let's move backwards from stern comp and compare something against SMNDF for my challenge, and that something is RAX. RAX is dereferenced from here, from whatever was in RAX. That was something added, RDX added to RAX. This RAX was a something that was moved from this var 50. The var 50 was, we scroll up here, initialized to the value of RDX, and RDX is the third argument to main, and the third argument to main is env. Boom. So we have the environment variable, and we are good there. So we see that this comes from the environment variable, and we have the value of the environment variable. So now if I go back to my terminal, I can see how to enter that in. That environment variable was smndf. and here we go, test. All right, so we hit SMNDF, it passes that, and then it says wrong. All right, so how do we track that as it moves through the program? So let's do a couple of, I'm going to show off a couple of concepts here. One is the concept of a cyclic pattern. So if I jump into IPython and I import pwn, and doing this live is going to be a disaster, but say a cyclic pattern is a bunch of data, let's say 64 bytes worth, where if you show any 4 bytes of it or any n bytes of it more generally, you can figure out where in the pattern those bytes came from, right? So you can imagine the simplest cyclic pattern is just the printable characters, right? If I put in this cyclic pattern and I say, okay, where in the pattern is capital Z, you can very easily determine that just by looking where in the pattern is capital Z. Of course, this scales to the size of the alphabet, but if I want a cyclic pattern of several megabytes, I can create one using pwn tools, and here it looks like every 4 bytes, if I say where in this pattern is XAAD, I can very easily figure that out. It's at offset 392. All right, why is this relevant? Because the easy way to go through this dynamically, rather than putting as an input AAA and seeing how that is mutated, is to put in a cyclic pattern. So let's actually put in kind of this simple one from 0 to capital Z. But in the general case, you can use pwn tools to generate arbitrarily long cyclic patterns. All right, so here's our input, run, no flag for you. Okay, now we need to start thinking harder. All right, so let's jump back into the Binary Ninja. What we have here is the comparison. All right, so it finds our the correct environment variable, okay, and then it says, okay, if it's the correct environment variable, so if strcomp returns 0, we jump here, and here we start doing something. Then okay, so here's the assertion that that we found the right environment variable. And you can tell that I'm not even reversing the code. I'm just looking at this string right here. That is the assertion that there was no environment variable found. Cool. So let's skip that. Let's go here. So here the environment variable was found, and we do something here. It looks like that messes up our input. And then here we're checking the received license key. Note, all of that I just said, I didn't go through and read assembly instruction by assembly instruction. I looked at string constants. I looked at code structure. This is some loop that evidently is mutating my input. This said env not equal to 0, which is what the program said when I ran it, right? So all of these little pieces that you recover from interacting with the program, from looking at different parts of the program in your reverse engineering tool, all of that should come together and synthesize in your mind, right? Awesome. So, all right, someone's asking on Twitch real quick, doesn't test RAX or test EX always return 0? Where was it? It was right here. Test is not comp. You're thinking of comp. The compare instruction, comp, does a minus, and then sets a bunch of flags. Test does an and, a bitwise and sets a bunch of flags. What does this mean? This means that if you test EAX, fundamentally you're checking, is the sign bit set on EAX? Is the 0 bit, or sorry, is EAX 0? You know, all of these things are properly compared, properly set. So test EAX, fundamentally what you generally see that used for is checking if a variable is 0. Cool. Let's move on with that. All right. So the remaining question here is, what does this loop do, right? And this loop, what we're going to do is look at it in GDB to see what this loop does. So first of all, what does this loop work on? It looks like well, first of all, the question is, obviously it will modify our input. The question is, where is our input? An easy way to locate our input is by looking at the final comparison. So here, our expected result, we've looked at this in the last in the lecture, how to find or how to look at that. But if I double click, as a reminder, here's the expected result. It expects the input to be CLAJXRQF. That's pretty cool. Oh, escape does work. My browser must have been screwed up. But the what that is compared against is our input in this var 19. var 19 is at RBP minus hex 11. So now we even know where our input is. All right, this should be everything we need to track. Oh, the other thing we need is the address at which to start looking at our input, right? And that address is going to be the base of our binary plus 1383. Cool. So let's do, back on the terminal, let's run this in GDB. Okay, we're in main. Actually, one thing that I want to get at the bottom of, if we are root, Connor, are you on one of the platforms? Doesn't seem to be on Zoom. It looks like on the yeah. So Connor just noticed that we need to. You'll notice that unlike on my machine, on GDB in the container, the address space layout randomization is always on, right? Even in GDB. This is because of this problem. We need to fix the way the containers are launched to allow this. In the meantime, we need to offset not off of a constant value, but off of this bizarre randomized value every time. So, but this is easy. I just say, okay, we are running with a base address of this. And now I can do stuff like break at base plus, I forgot the offset there. It was here, right? Yeah, this is after we have passed all the checks and basically are sliding in to our mangling loop. So 1383, OX1383. We have our breakpoint, and then we can run. Let me get the environment variable. Set env set. I'm drawing a blank. One sec. This obviously doesn't work. Yeah. Set env. Okay, this is where I embarrassingly enough, I Google this. That's okay. People draw blanks all the time. GDB set environment variable to run program. Set environment var name value. Perfect. Okay. There we go. Even I don't remember things often. All right, so here we are in GDB. Set environment SNDF test. Okay, or not test. Let's get our cyclic pattern, our homebrew cyclic pattern, because pretty sure this is long enough for level 2. Okay, and now we run. Yes, we will restart it. It re-randomized. Info proc map. Set base to this. Okay. We'll disable breakpoint 1. Oh, there is no breakpoint. Oh, we disable breakpoint 2, and we will set. We will break Facebook. Okay, and let's continue. Okay, so now we're at the breakpoint in main, right? So as a reminder, RBP holds our RBP minus 11 is where our data is. That's interesting. It seems to be let's jump back to Binary Ninja. It was RBP minus 11, right? RBP minus hex 11. And we are here. RBP hasn't changed. Oh. No, that is not where our data is. That is where a pointer to our data is, obviously. Okay. So, string comp takes a pointer to our data, right? And that pointer is... No. That pointer is RAX. Where's RAX set? RAX, the load effective address of RBP minus 11. This should... Oh, hex 11. I feel very silly. That was a noob mistake. But this also doesn't work. So let's just look on our stack where our data is. No, hold on. Yeah. Let's just look at, let's say, 64 keywords of the stack and see if we see anything that looks like our printable data. No, wait. The data should be in the environment. So this should be RBP minus 11 should be a pointer, right? So let's take a look again. So if we move into RDI a pointer RAX, that RAX is loaded. It's the address of RBP minus 11. Is RBP not a frame pointer? Nope, RBP is a frame pointer. Oh! Move. So here it's mangling bytes, reading and writing. Okay. Here, it gets one keyword, 8 bytes, out of RBP minus 20, moves that into RAX, adds 10 to it. So let's look at RBP minus 20. That's a pointer. Here's RBP minus 20. That's a pointer. That's pointing to our input. Okay, that's our environment variable. Amazing. What do we do with this environment variable? We add, we take that pointer, we add 10 to it, and then we dereference that and read 8 bytes out of our string, 10 bytes into RAX, and then store that at this variable 19, which is RBP minus 11. Okay, let's take a look at how that looks like. So let's add a display. By the way, I'm doing this in generic GDB. I really hope you're using pwn.debug or Jeff or something to make your lives much easier. Okay, so, oh God. I'm sorry about this. Disassembly format until dash format. One sec. Disassembly flavor. Okay. So let's get that back in Intel format. Here we go. We're about to look at read out this variable. Let's step. So now that's an RAX, and RAX is now our string, pointing to our string. Then we add 10. So as you can see, RAX is now pointing here. What is the location of the number 4 in our string? Well, that is nice and easy. We can hit IPython. Here, that index 4. Oh, look, it's index 4. Of course, you know, that's easy, but Z is index 61, etc. Right? Cool. Okay, so then we can, let's background that. All right, now we're back in GDB. So as a reminder, oops, here's RAX. Awesome. So now you can go to the next instruction. Now, well, we missed the last instruction. What it did, the last instruction was about to dereference that. So read a value out of RAX, out of what was pointed to RAX. So let's take a look. Here it is. It is a printable bunch of printable data. Hex 34, that's ASCII 4, ASCII 5, ASCII 6, ASCII 7, ASCII 8, ASCII 9, and then lowercase a, lowercase b. Very cool. All right, so that's great. Now, what are we doing with that? We're going to write it to RBP minus 11 finally. Step, now it's an RBP minus 11. So now, hex 11, here it is. This is the data that's going to get mangled, right? That's incredible because we can take a look and we can see that, right? This RBP minus 11 right here, this shows up all over the place. Here it shows up as a read, so it reads into EAX, then it does something with it, and then it'll write, also offset by RAX, so it looks like there's, you know, some tricky offsetting that's going to happen, and it'll write into it. Okay, let's go back to our terminal. Now that I have the data and I know where it is, I can say display it every time we stop RBP minus hex 11. And now it's added to the display. So now if I start stepping, well, let's just use next instruction. Let's not jump into, I mean, there are no function calls that I glanced at, but next instruction will step over function calls, which was great. We don't want to get stuck in, you know, the minutia. So now we just start stepping, right? And we're going to keep stepping until we get out of the loop, and we're going to see how that input changes. And the loop, getting out of the loop is going to be when we reach 13E3, right? Until we and this load effective address of with checking the license key. So until then, we're gonna just keep stepping. Right, and at every step you can see how these change. Right, so let's just keep stepping until it changes once, and then we'll see how. It's not changing. Oh, it changed. It changed. I was just staring and okay, it was on autopilot. So here's an interesting one. It was 4, 5, 6, 7, 8, 9 AB, and suddenly it became B 6, 7, 8, 9 AB. That's interesting, and it became that around 3D5 is what ended up. No, sorry. Here. 3C3 is what ended up writing to that, because when we stopped before this instruction, it was 4, 5, 6, 7, 8, 9 AB, and afterwards it was B 5, 6, 7, 8, 9 AB. Okay, if we keep stepping, I bet this might be a swap, and it was, right? So we probably had some temporary variable that hadn't been written yet, and now it's B5, 6, 7, 8, 9, A4. So we can see that we swapped the first and the last variable. If we go back now to Binary Ninja to confirm our suspicions, we can. I wonder if I can increase the font size. No. Okay. Anyways, let's keep rolling. All right. Here we have so let's do some renaming. This var19 is really our input. Awesome. So now we have our comparison between our input and the expected result. Here our input gets read into EAX, and then AL gets read into this byte. So this is byte of input, right? All right. Now what? Then EAX, we move OX7 into EAX. We subtract from EAX this var minus 2C. And what is that? This looks like a counter that is initialized at 0 and is compared against 3 before it jumps. So this is our counter. Incrementing counter, it looks like. Because here you can see that it's incremented by 1. Okay, and basically we have almost all of the mystery solved. So we read 1 byte of our input, put it into EAX, take that byte ends up, of course, in the least significant byte of EAX, and AL references the least significant byte of EAX. Put that byte into the byte of input. We write 7 into EAX and subtract from 7 the incrementing counter. So it looks like 7 seemingly is, in this case, is referring to the position of the byte to swap, probably. Because we can see that it is later. So here, the index is used directly. It's loaded into EAX, and then it is used as an offset to where to read the byte from. It starts out as 0. And then here, the EAX starts out as 7 and then subtracts from the index. So it's swapping the first byte with the last byte of our input. And that's what we observed. And then, of course, as the counter gets incremented, it'll swap the second byte and the second to last byte and so forth. We can basically see that it here is the read for our input. So let's just make a comment. I wish there was a hotkey to make a comment. Read a byte of our input. Okay. Here is where it'll read a byte at the end of our input. So it here is read another byte of our input. Shit. Here. Yeah. read another byte of our input. Okay. Awesome. So what does it do with these bytes? And here's the other, okay, other byte of our input. It stores it right there. Okay. Cool. Then we read in the incrementing character again, and then this reads the other byte of our input stored on the stack into EDX, and then writes DL into our input here. So here we write other byte into the first byte. So let's give them names. Instead of byte of input, let's call them what should we call them? Let's call them apple and orange. We have an apple byte. So the apple byte is stored here, and then we have orange byte. Okay? And of course, apple and orange, they don't have semantic meaning here. I don't have semantic meaning yet for what the hell is going on. But I know that these are two different bytes that I read, right? So I make names to try to keep them semantically different in my in my head. Yeah, okay. The Zoom is telling me to increase my the Twitch is telling me to zoom in on my browser, but I guarantee you. Oh, well, I was gonna say I guarantee you that'll mess up the. It did. Now I can't go all the way left. So, yeah, that was not good. Okay. Anyways, we can. And if we, then there was also. Oh, amazing. There is a hotkey. It's semicolon to make a comment. I had not found that. Now I do. Now I have. All right, cool. So we have apple byte and orange byte. And what we can see is we read out our orange byte. And then here, let's just say, okay, now the insanity starts. Because that's, you know, we here was the read of another byte. Here was the read of our first byte. This is calculating the index of orange, right? Calculate index of orange. And this was calculating index of apple. Okay. And here, the insanity starts. So we don't know what's going on yet. So first, we get our incrementing counter into EAX. We get our orange byte into EDX. And we store DL into RBP plus RAX. So DL is our orange byte. And we store it to RBP plus RAX plus OX11. What is RAX? RAX, EAX. We just read here. It's from the incrementing counter. And that RBP, this RBX minus plus RX minus 11 with just incrementing counter is exactly how we read out, gosh darn it, right here, how we read out apple, right, into EX, and then wrote that into the temporary storage. So this overwrites what used to be our apple byte with orange byte, right here. So overwrite apple byte in our input with orange byte value. Okay. And then we can see we do kind of the same thing. We get 7 out, and you can kind of pattern match. This is how we computed the offset for orange byte over here. We subtract it, and then we read out the saved apple byte, and then write it into the orange byte. So overwrite orange byte in our input with apple byte saved value. It's a swap. That's it. And we observed that dynamically, and we could have probably just been happy with that. But now we went back and we reverse engineered it on the assembly to see what is going on. And we can see also from the assembly that it's going to swap. It's going to do 0, 1, and 2. Because the moment it is not less than or equal to, and 3. As long as it's less than or equal to 3, it is going to happily keep doing it, right? So the expected value, the expected result is CLAJXRQF. So let's try to run it with, no, what was the environment variable? Okay, and don't forget, it actually offsets 10 from here, 1, 0. So sorry, this is, if it offset 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that should be sufficient. And then we will take the expected value, which was, oops, I'm not on the terminal. All right. Cool. Okay, here we go. The expected value is CLAJXRQF, but of course, we need to swap some things. We need to swap 4 bytes worth. So here's F and C swapped. Here is Q and L swapped. Here is R, oops, what was that? R and A swapped. And X and J swapped. Okay. And then we call Abraf Testing, and it's wrong. So let's figure out why it's wrong. Let's go back into GDB. Let's grab this. What's going on? Why? Okay, here we go. Okay, so we tried to do this. Awesome. Then let's disable breakpoint 3 because that's gonna get re-randomized. Here we go. We start out, we're back in main. RBP minus 11 doesn't yet exist, of course. Let's info proc map, set base that, oops, equals that. Break at base plus OXR. All right, and then continue. Okay, now let's see what gets loaded into this RBP minus OX11. Okay, it looks like I added one more A than intended. Cool. Okay, let's take off this one A. Boom, flag. Okay, so that's generally how you approach this entire set of first 10 levels or so. Of course, you have to figure out how the program is taking input, have to figure out the offsets, have to figure out the specific modifications. But with a combination of static and dynamic analysis, and it's very, very important, you're not just using the tools to solve stuff. You're using the tools to get information that you are then synthesizing in your brain to maybe build an understanding of the program step by step that will allow you to mount the attack or whatever, to synthesize the answer, to understand, to get the flag. All right, awesome. There's a question about FIFOs. FIFOs are pretty simple. I mean, you know, everything is simple if you understand, if you have already experienced them. I understand that, but FIFOs, once I explain it to you, should hopefully be pretty simple. Let me stop all this. Okay, for FIFOs, I'm going to spin up 2 terminals by using screen. So screen is, what the hell? Screen bin bash. I didn't think that had to be specified. Screen is an amazing program that lets you basically, that lets you have multiple terminals. So this is, or multiplex a terminal to multiple terminals. This is terminal 1. I hit Control A, N. This is terminal 2, and I create it with Control A, C. All right, awesome. So let's create a pipe. I'm gonna create a pipe named Jan. All right, that's not very creative, but whatever. And this is just a FIFO rather. This is just a special type of file. You can see this weird P over here. It's because it's a FIFO, and FIFO stands for first in, first out. What does that mean? That means on one side of the FIFO you will send a byte. On the other side, you will read a byte, and it will read in order that it received it. It's the most basic sort of communication mechanism. You just send bytes on one end and receive them. So how do I receive them? Or how do I send them? I send them like normal. Send them echo hello. So of course you could do hello, and you could pipe through cat, and that'll cat it read from standard input, which is hello, and write to standard output. Or in the same way, exact same way, this is an unnamed pipe, and this is a named pipe, right? In the same way, I can redirect to Jan. So now it's hanging. Why is it hanging? It's hanging because it's waiting for something to read that data. I go to my other terminal, and I read the data. So here is my named pipe. I can just cat it. Boom. That data was read. Go back to the other one. It happily finished reading, and it's done. Same way, I can, if I go and cat Jan when there's nothing writing to that data, it sits there waiting for data. And I do this, and here it is. All right. Why are FIFOs useful? Right. One, they're a useful way of getting moving data around. FIFOs, you can have pretty clever uses of them. Like you can have multiple things reading from a FIFO at the same time. It's one way to do job dispatches. So let me, there's a command in bash seek. It'll just count from this. It'll do a sequence from 1 to 10. And I can push that to the FIFO. And if I cat it, here's the 10. So let's do seek. And then trying to think of a way to, well, actually, we can make this arbitrarily large. Okay, so obviously, if I cat that out, this is going to take a very long time. But if I create 2 children that will read from that pipe, here's one. It's reading. Here's the other. They're reading different values. I mean, they're taking turns reading values from the pipe. So if this specifies a bunch of jobs to run, then the 2 cats that I have running will each pick some of those jobs, some subset of those jobs to do. So it's a good way to do a multi-processing queue, for example. I can kill that, and then right away these guys are done. Pretty awesome stuff. All right, that's one thing. There's some things you have to be careful about, buffering and so forth. Another interesting reason to use a FIFO in reversing specifically is you can use it to hang a program. Right? Let's say you have a program like cat that automatically reads and files and does stuff, and you want to run it outside of GDB, but immediately have it stop. If you redirect, if the program reads from a standard input or from a file or something, for example, you want to debug GCC, right? But GCC takes a C file, right? You can create a named pipe named yan.c, and you can do gcc yan.c, and it hangs. And now you can attach to it with a debugger and look around. All right. Hopefully that answered the FIFO question. We have a question on Zoom. Yeah, go for it. So the question was, um, a FIFO opening program will require a specifically named FIFO. Yes, you will have to do that from a different terminal. Interacting with that program, you can SSH in twice, right? You might not be able to. You can't SSH in twice using the web terminal front end for pwn.college, but you can use that and then use screen to multiplex your connection, or tmux. All right, go ahead. Yeah, absolutely. You can SSH from multiple terminals. Nothing stopping you. All right. So another thing we're gonna jump. Someone on Zoom asked. They thought it was Control A and N. Yeah, it is. Control A N, Control A P, Control A C to create a new one. Screen is amazing. tmux, if you're a mega hipster, tmux has some drawbacks. It in some cases is not as performant as screen, especially if a program goes crazy and starts spamming your terminal. On the other hand, screen sometimes has memory corruption and sec faults. So yeah, it's a trade-off. Connor on Twitch is memeing here that tmux was released 12 years ago. That's like yesterday, basically, man. All right. Anyways, let's move on to level 11 real quick. So internally, we have our names for these levels. Where's my terminal? There. Yeah. So internally, we have names for these levels. Level 1 through 10 are baby key. They're key generation, right? And then level 11, you get a very rude awakening. So that's what's going on. Why isn't this working? Oh, I got logged out. All right, level 11. We get a rude awakening. Let's start it up, and of course, open it in Binary Ninja. I gotta say, Binary Ninja, it takes some getting used to, but this integration I really like. Just being able to click on inspect and it opens it up. Good job, Connor. That is great. All right. One thing that we're going to see, of course, the teaching levels are a pain in the butt to reverse because of all of these cost of puts. But one thing that we'll see right away in level 11, so here's where the mangling is done. Here, nope. Yeah. Boom. MD5, right? That's bad news. Okay, let's take a look on the terminal. What the heck happens? Okay. Interestingly, before it reads our input, it allows us. It warns us this license key cannot be reversed. Right, you'll have to crack the program. So let's just okay, cool. Go away. So we get 3 bytes that we can change, and then it takes our key as a command line argument, our license key. Yeah, say hello. Okay. Okay. The data was read in. Wait a second. Where did this come from? let's just on. We skipped. We skipped 10 bytes, and that's now in the environment. Let me just show you. Okay, so if we replace it with, okay, here's this string, and we unhex it. Oh. Pro tip, you can pip install fuckpy3. It's an incredible... No, you can't. God damn it. Alright, now I have to actually remember how to do this without my tools. I think it is bytes from hex. Yeah. Okay, yeah. So we skipped 10 bytes and ended up reading from our environment. That's silly, but let's just put a bunch of A's. All right, cool. Okay, so it read in a bunch of A's, and then it mangled our input with the MD5 mangler. So literally, MD5 is our input. The resulting data is this. This is our MD5. And to verify that we input the correct license check, it'll compare it against this MD5. All right, so you might say, okay, well, shit, I have to crack MD5. I have to figure out what the value, the input value needs to be to MD5 to this. This is not the right way to solve the problem. A lot of students are approaching this like that. They're completely ignoring what this challenge asks you to do first, which is, hey, you can change data. So if you remember, one way, when I talked about keygens and so forth, one way to bypass a keygen is just modify the program directly. Here, you can change an offset in the file, in memory, in the loaded code, and change it to whatever you want. You get 5 bytes. You can do a lot with 5 bytes. Imagine all of this. You can change anything here, right? And of course, your challenge is to get to here. So can you change 5 bytes in the binary to get to that point? Yes, of course. Awesome. Okay. Other questions? We have like 4 minutes left. Oh, question on Twitch. Can you change the text segment? Let's take a look. Let me load up the testing instead of the teaching, because it's easier to reverse without all those print statements. And let's spin it up, because I'm gonna show you. All right, let's see. What does it do? It first loops and protects a bunch of stuff. That sounds pretty promising. Let's grab a terminal, SSH in. If we strace this guy, protects this address, read, write, and executable. Okay, that's interesting. If we do a proc 47 maps, wow, there's a lot of stuff in here because it links in crypto. Oh man, my terminal's messed up. Hold on, we're gonna have to reset the terminal. Okay, and now do that again. Now that scrolled off. Anyways, let me just restart it. Okay. All right, we strace it. This is what it is working on here. Let's, well, obviously it's not going to be the same. Proc 55 maps. Okay. The address of the main binary of the text segment. This is the, well, actually you can just see it. It's now read, writable, and executable. So yes, you can change the text segment. The binary explicitly allows you to do so. Oh, sure. Let me spin up level 14. Spin it up in practice mode and open the inspect. Okay, so level 14 is the beginning of baby VM, what we call internally. Baby VM is a virtual machine that I wrote. It was originally Connor's idea to convey the core art of reverse engineering without just staring at decompilation, without just trying to look at bytes being swapped in GDB, to try to understand something new. And that something new is Yan 85, the architecture that we created for this insane challenge. All right. So let's take a look at a high level on what level 14 does. Level 14 says, okay, prints out an introduction. Great. Then it does some setup. It disables buffering. Buffering is a giant pain in the butt. And it says there's something called VM code length. There's something called VM code. It mem copies VM code somewhere, and I guess it'll copy it here. New VM code dest. Okay. And then it loads VM code dest into RAX, loads RAX into RDI. Of course, this was compiled without optimization, so there's a lot of weird redundancy in the code. Then it calls the interpreter loop. So, oh shit, it's some kind of interpreter. The interpreter loop, very simple. It goes instruction by instruction, or in a loop, it calls something called interpret instruction. And you can actually see that it where is our, here we go. RDI was our, if you go back, RDI was the argument of our VM code. So here, let's say this is our VM code. And it looks like it goes through and it loads a bunch of stuff from VM code, and it calls interpret instruction. Interpret instruction. This is kind of a typical interpreter, like a handler function. It does a bunch of checks and then calls the handler function that that coincides with that passes the associated handler function to the check that was successful. And you can see immediately from the names that there are several. So the fact that this says interpret instruction, we know, okay, this is an instruction that is being interpreted. This seems to imply that there are several different instructions. This is an immediate instruction, im, an add, a stick, a stum, a ludm, a compare instruction, that should be familiar from x86, a jump, should also be familiar, and a sys. All right, let's look at im. Super straightforward, seemingly, right? We read this instruction does some stuff and then calls write register. And what does it call to send to write register? It sends RDI and RSI. Obviously, first and second argument. Is there should be an RDX that it sends. I'm sorry, what? REX is not a parameter. So the calling convention, if you recall, RDI is the first argument, RSI is the second argument, REX is the return value, RDX is the third argument. So write register, if you look into it, this is again a typical structure in interpreters. This is a switch statement. This is what a switch statement looks like. And the switch statement has case 1, case 2, case 3, and 4, and so on. Or it looks like 1, 2, 4, hex 8, hex 10, hex 20, and it compares against hex 40 here. There should be one more. Oh, interestingly, how this optimized it. All right, so you can see, okay, write register. An interesting thing. We saw interpret instruction, or sorry, interpret loop calls interpret instruction. We drill down, interpret instruction calls these individual handler functions. We drill down. These handler functions, this interpret im calls write register. We drill down. What does write register call? Write register calls crash, which it calls with unknown register. And that's it. It doesn't call any other function. So this, in some sense, conceptually speaking, is the deepest level of our of this binary, right? You know, everything else calls deeper and deeper and deeper. This doesn't have any deeper to call except for this crash. Let's look at the crash. The crash says machine crash due to blah, printfs, and then calls exit 1. Okay? All right. So this is a giant pain in the butt. When things get really crazy and you just need a high-level idea rather than understanding exactly byte by byte how everything works, and a high-level idea is a very good idea. It's a very good thing to develop early on. Switch to high-level IL or hit the decompile button in IDA. Switch to this source view. This might be a little easier to look at. Maybe not. So this is, you can see, okay, if this RAX1 is greater than hex 20, and if it's not equal to hex 40, then it crashes. So it has to be either hex 20, or it has to be either hex 40, or less than or equal to hex 20. And then here, say, okay, if it's less than 0, it also crashes. This label 1434 is here. If it is greater than hex 20, this is the decompiler being a little weird, also crashes, right? So it has to be less than or equal to hex 20 at this point. And then we do a switch statement. We say, if it's case 1, then we have this, we take the first argument, which is seemingly a pointer because it's later dereferenced. We seek into it, or offset into it by hex 3FF, and then we write some value determined by var18, which is the third argument. Okay? So we write something derived from the third argument into an offset from the first argument. Where's our second argument? Our second argument went into this RAX1, which is used as the selector, right? So it looks like the arguments are some state, some structure that you will end up writing to and write register. That's interesting. And remember this offset OX3FF. It'll become important later. Some value that is used as a selector. And then some value that is written, right? So write register, you can imagine, based on the name, the value that's used as the selector is some register selector. All right, remember it's 3ff. There's another another function called read register. Let's dive into it. This is already the decompilation. Is 3ff here somewhere? Turns out yes. In read register, also in case 1, also checked by arg2, we dereference and load this 3ff, right? Of course, this is a kind of disaster scenario here. It's the decompiler not being very helpful. That being said, you can kind of see it first reads it as a D word, 4 bytes, and then expands it into a Q word, 8 bytes. You can also see a little better on the low level. No, go. If you look at the assembly of read register, if you look at case 1, this is more readable in this case, right? So the decompilation often is easier to get a high-level structure, and then to actually understand the facts without going insane, you can look at the disassembly. So here we have this var10, which I guess came from here, which is RDI. So that's our first argument, right? So this, let's say, let's just, okay, now my hotkeys don't work. Am I in caps lock or something? No. I can't rename this. That's interesting. Can I rename this guy? Yeah, this guy can rename it. All right, I don't know why I can't rename that. But okay, so basically this is some structure from which we take a pointer to it, write it to our var10. This var10 we then read into RAX. We offset RAX by OX3FF, read a byte from that, this move byte. 0 extended the byte as a signed byte, and then we jump here, and if we double click here, we jump to 135B, and that just returns, right? RX is the return value. So this returns a byte from some structure. Now, the function is called read register, so it seems like this arg1 is you know, the register number, this case 1 encodes what register to read. 3ff is its offset in a structure, right? So now we say, okay, let's change the type of this guy. Actually, I've never done this in Binary Ninja. Can we create a type? Create new types, okay. Type, all right, so we have at OX3FF, so let's create a struct VM, and we have some unknown stuff. So we have some unsigned char something. Then this is hex 3FF in size, and then we have unsigned char register 1, right? Hit create, and then let's just to be safe, we'll create something else here. Okay, you'll see why. Create. Okay, so now hopefully if I scroll down, it's there. Where is it? Struct VM. Okay, awesome. And then I can modify it and so forth. All right, so now we created this struct VM. Let's go into read register. Go back into read register, and we say, hey, let's change this to type struct VM. And suddenly, boom, that makes a lot more sense. VM register 1. And this is VM something a little earlier than register 1 at 3FE. This is the second byte of that something else. So then I go back and I start filling it out. So the second byte of something else means something. The third byte of something else means something. The second to last byte of something, the third to last byte of something, and the 0th byte of something else. So something else obviously means something. Let's go back to those types. Scroll down to VM. Do the change type here. So there is, interestingly enough, it converted this from OX3FF to 1023. So uint8t, it also converted my unsigned charge to uint8t. That's equivalent. It's an 8-bit unsigned integer. All right. Here is register 2. You can give them names if you want. You can name them after fruit. Register apple, register orange, register mango. What's another register? Banana. Plum. I don't know. Whatever, right? You can keep going. Create a bunch of them. Because you don't know their semantic meaning yet. You know their registers, right? Everything else is meaningless. And here, suddenly, say, okay, did it not save? Do I need to reload this somehow? Go back out, go back in. There we go, okay. Here we see this is reading register apple. This is reading register mango. This is reading register banana. This is still reading, this is register orange. We don't have register plum, so I guess I should delete register plum, probably. But there's still some things missing here, and those are the last 3 bytes of this something up to 3FE. So let's go back. This is the process of reverse engineering things with structures. There's just no... I mean, the UI could be slightly better. Where's my VM? There it is. Change type. So let's make this 20 and then uint. So earlier in the structure, there's some more registers, obviously. So register tomato. I need 3 of them because I just took 3 bytes off of the size of that structure. Register tomato, register celery, and register grape. Cool. Okay, create that. Go back. Leave the function, re-enter the function. Here we go. Register grape, celery, tomato, orange, apple, mango, and banana. Amazing. We have figured out exactly what this function does. Right? It takes an argument and a VM, a pointer to a VM structure, and then switching based on the value of the argument from, and looks like a bitmap. This is 1, 2, which is the least significant bit being 1, everything else being 0, 4, the next bit being 1, everything else being 0, 8, and so on, right? It reads the correct register. If you go back to write register and set the type here to struct VM, I bet it's the same thing. This writes register apple. So you can see it writing register apple. This writes register grape. This writes register mango. Pretty amazing, right? Register banana, and so on. Now let's look at a different thing. So let's say, okay, if you go to interpret instruction, interpret sys sounds pretty suspicious, right? I think the hip people now are saying sys is sus, or sys sus. Anyways, you go to interpret sys. This looks like a crazy thing, right? But it's interesting in a couple of ways, right? It calls open, can call read, can call read again for some reason, can call write, can call sleep. That's pretty cool. Sounds like a way to interact with the system. Now I wonder, of course, all of these are called roughly in the same way. Here's RSI and RDI being set, and RDI is set to this var10 variable that is at RBP minus hex 8. And it's the same for comp, and it's the same for sys, right? So the type of this variable seems to be the VM. Oh, it already figured that out. if I go into interpret sys, RDI, the first argument to seemingly the interpreters you looked at so far, where's RDI, is VM. Yep, it figured that out. At some point, binary integer gets smart. And here's an interesting thing. When open gets called, open, of course, if you remember, this is a libc function. It's an external function being imported from libc. We're outside of the VM, we've dived in, reverse engineered some stuff, and now we've dived back out. When this gets called, of course, you know open. You have done man open a million times, right? Man open, boom, path name and flags, right? Let's dive back in. What happens? Path name gets passed in RDI, flags get passed in RSI. RDI comes from RCX. RCX comes from is added to RSI. RSI is some crazy RCX plus OX2FD. You'll have to reverse engineer and see where that is actually pointing to. And if you go all the way back here, no, sorry, hold on. RSI comes from EAX. EAX comes from, why is it saying command failure? All right. From AL. AL comes from register celery. So it looks like by setting up your registers inside the VM properly and calling the sys instruction, you can cause system calls, right? So that's pretty interesting already. So already we have a lot more. We've been looking at this problem for 20 minutes. We have a lot of insight already. There are registers in this machine. We know the encodings for these registers. We have register apple, mango, blah, blah, blah. We know that registers celery, grape, and tomato are somehow used when we're calling open. We know that when we call read, we use celery, grape, tomato, and and those three again. When we're calling, here's an easy one, exit, it looks like we take, exit takes one argument, RDI, the exit code of the program. Super simple. All it looks like we have to do is set, so we move EAX into EDI, we move AL into EAX, and into EAX we read register tomato. So it looks like register tomato is the exit code when you call exit the system call. So now, of course, we have to put this together with interacting with this program dynamically, setting GDB breakpoints in various handler functions and so forth. We're already 20 minutes over time, and Baby Jan is starting to fuss out in the rest of the house over there, and we'll soon start throwing tantrums. So we won't go into that right now, but maybe Connor can dive in office hours as well. All right. One other question from Zoom. Someone has reverse engineered the sorting function, understands exactly how it works, but how do you approach the problem, right? This is for, of course, levels 1 through 10. There is an intended input that will make it through the sorting process, that starts out unsorted, will make it through, come out sorted, and then pass the other checks, right? Pass the, the whatever, compared against the expected result. You don't give a shit about that intended input. All you want is one input that will work, right? So think about it this way. Can you reduce the sort to something that's completely irrelevant? For example, what if your input was sorted to begin with? Cool. All right. Any other last minute questions? Otherwise, we will call it a day. And as a reminder, Connor is holding his office hours tomorrow. Those are at 3. No. Back up. Those are at 2 p.m. he'll answer plenty of questions. Someone asked on Zoom just now, can we have more office hour times? That's a hard ask. Just kind of as a look behind the curtain, with the amount of stuff that we all have to do, including, you know, not just teaching but research obligations and so forth. Connor and I are already sleeping like, I don't know, 4 or 5 hours a day. At least I am sleeping 4 or 5, or usually less. And Connor always seems to be online when I'm online. So it's tricky. We'll see what we can do. I think one thing that we will do is move Connor's office hours to Friday. We're still making sure or he's still making sure that it works with his schedule. But but in terms of extra office hour slots, I don't think I'll be able to schedule them. My wife is only willing not to see me for so much, but we'll figure out if we can maybe do something where we have an extra collaboration hour slot, or something along these lines, so that you can at least work together to solve some things in the beginning. We'll figure it out. Cool. All right. Thank you for joining. Good luck with the challenges. And we'll see you on Wednesday for memory corruption. Or also, don't forget to call into Connor's office hours tomorrow. Good luck.